Okay, whenever you're ready, Antonio.
Okay. Can you see the presentation?
Yes, we see the presentation.
Okay, thanks. Okay, we were here. So we were telling that if we acquire data at different polarimetric, at different polarizations over the same scene at the same time, as for instance, thanks to full polarimetric search sensors, we are able to see different things of the scene, okay, of the targets in the scene. For instance, here through the HH polarization, see the cables, and through the VV polarization, see the pylons of the high voltage structures that are present in the scene. We can extend this example and think that the combination of the data acquired at different polarizations, so by means of full polarimetric SAR data, allow us to extract information about the scene also in really complex scenarios, extract the physical, not only geometrical information of the targets through the proper combination of this data. Okay? But we need to somewhat formalize the quantity we measure. Okay? And a convenient way to formalize the scattering process is to resort to stochastic quantities, that is, treat the electromagnetic received field as a stochastic process. And through this, exploit synthetic statistical descriptors of this process, like for instance the mean value or the so-called coherent field and the variance or the so-called, in other terms, incoherent field to describe, to catch the fundamental aspects involved in the scattering process. Okay? Okay. Okay, let's start from the transmitted wave. We told before that we transmit a field, an electromagnetic field that propagates along the key direction, and where the electric field lies, the vector describing the electric field lies in the plane VH plane. Sorry, I forgot the pointer. The electric field, the vector associated to the electric field lies at a great distance from the source in the plane orthogonal to key. Okay, the so-called equiphase plane. Okay. And while the wave propagates along the key direction, it in general describes an ellipse. Okay. And if I observe the transmission in a moment, given the relationship for a fixed relationship between the H and V components of the electric field, I will see that the shape of the elliptical pattern in general will not change over time. That is, the properties of the transmitted field do not vary over time. Okay. I transmit in each component and a V component of the electric field, and this the relationship between these two components will not vary over time. Okay, for instance, if they are in phase or in phase opposition, I will transmit a linear polarized wave. Otherwise, if I transmit an electric field whose V in each component have the same amplitude, but the phase is such that they are in quadrature, we will have a circular polarizations. These quantities will not vary over time because these quantities are dictated are ruled by the transmitting device. So the incident wave is completely polarized. Its characteristics does not change over time. Okay? But when the waves imping on the targets, part of the energy is absorbed, of course, part of the energy is directly backscattered toward the sensor, but there it may happen also more complicated things. For instance, here there is a double bouncing of the wave. Here is a chaotic scattering mechanism, so that the wave that from this part of the scene goes back to the sensor comes to the sensor after strange scattering phenomena, complicated scattering phenomena. So we can expect that the characteristics of the transmitted wave are not fully retained. Okay, and indeed, the scattered wave is characterized by a cross-polarization degree, that is, part of the energy moves from the H component to the V component and vice versa. And moreover, the relationship between the two components is not fixed. Their characteristics may vary over time. So, for instance, with regard to this aspect, the phase, if I transmit H and V components that are in phase in transmission, I have a linear polarized field. After the scattering, I could have that this phase relationship is not still retained, is not longer retained, and the field is no longer linearly polarized. Okay? This quantity, the polarization may vary over time, the polarization state. And we usually call this phenomenon, we measure this phenomenon with the polarization degree of the waves received by the source sensors. Okay? We transmit an incident wave that is completely polarized. The characteristics do not change over time. What I measure at the receiver side, at the radar side, is something that could be cross-polarized and depolarized. Cross-polarized, part of the energy moves from V to H or vice versa. Depolarized, the relationship between the two components may vary over time and is in general not equal to the one of the transmitted field. Okay, of course, this phenomena depends on the targets on the ground. The more chaotic is the scenario, and more cross-polarization and depolarization I can see in the data. Okay? Okay. Just to introduce you that what I measure and at the receiver side is not necessarily equal to what I transmit. And this is a good thing, because through this information we can through this effect we can retrieve information about the targets. Okay, again, we need a mathematical framework to describe these effects. Again, we have to resort to the radar cross-section or to the normalized radar cross-sections, through which we can define the called scattering coefficients. Okay. In general, if we deal with a complex target, okay, the yellow one, where that is illuminated by an electromagnetic field at a given polarization, I can describe this target, this distributed target, as the superposition of a lot of elementary targets, okay, with differential RCS, the sigma, okay. Through this, by performing an average in statistical sense, I can obtain the normalized radar cross-section or the cross-section of the quite complex, not ideal targets I'm considering. Okay, sigma naught and sigma, NRCS and RCS of the target. E is the area of the target. Through this, I can define the scattering coefficients, okay, S, which substantially are equal, if you remember the slides, the part of the talk on the calibration, the sigma naught, the RCS depends on the energy, the amount of energy that goes back from the target toward the radar. Okay? So this quantity, that is the incoherent field, the power of the electric field described as a stochastic process. Here, the brackets represents the statistical mean, is substantially the power that goes back toward the sensor after the scattering process. The upscript S is for scattering, normalized to the incident power. Okay, substantially, this quantity defines the scattering define the scattering coefficients, okay? And then the RCS and the sigma naught, the normalized radar cross-section. Okay, this quantity depends, of course, on the polarization. Okay, I can define a scattering coefficient for both the transmitted polarization H and V and for both the received polarization. Considering one transmitted polarization and one received polarization, I define a polarization channel. Okay? For instance, in this notation, Q is the subscript related to the polarization or the incident field, and P is the subscript for the scattered wave. Okay? So SPQ is the scattering coefficients that give me an idea of what happens when I transmit an incident wave at the polarization Q and I receive in the polarization P. P and Q, both of them can be equal to the H component and V component or the basis we defined before. Okay. Before we just said that the wave propagate along this direction key, and V and H are two orthogonal vectors that lie in the plane orthogonal to the key direction, where also lies the electric field. Okay, we just said this. We didn't say anything else about H and V. Okay, they could be any couple of vectors orthogonal each other in this plane, orthogonal to the key direction. If we are interested in characterize the scattering, we have to define in a more precise way these vectors, these directions, okay, the basis for the scattering. And as for the scattering point of view, how we do this? If we are interested in the backscattering direction, that is the propagation followed by the scattering wave, is this one, is key, okay? Not the generic one in the space. How we can fix H and V? Okay, we can do this way. We have the propagation direction key. We can consider the normal, the mean normal to the observed surface N, and say, okay, the V component, the V vertical polarization is the vector. This is the direction orthogonal to key that belongs to the plane defined by key and then by the direction of propagation of the wave, the line of sight, in other words, and the normal to the surface. Okay? V is the vector normal to key that belongs to this place, to this plane. Starting from the definition of V, we can define H that is orthogonal to this quantity. Okay? H is orthogonal to V. After the definition of V, as I told you before. Okay? So we fixed both the vertical and horizontal polarizations as for the scattering point of view. Okay? Based on this, we can finally write the electric field, scattered electric field, in this way. Okay? That is, we can relate the diffuse field from the scene, the field scattered from the scene, in function of the incident one, both of them, of course, has the two components in the H and V direction, through the scattering matrix. Okay? This term is the propagation term, okay? Has no impact to describe the scattering properties of the scene, or the targets in the scene. This is just used for interferometry, or when you are interested in to retrieve geometric properties related to the radar to target distance, okay? For now, we don't care about this, the propagation and spread loss term, the spherical wave contribution. Okay, don't care about this. Let's focus just on this matrix that allows us to move from the incident electric field to the scattered one. Okay, who is the generic element of this matrix? Okay, I told you before. SHH, for instance, is the scattering coefficients that give me information on the scattered field at the H polarization when I transmit the H polarization. SHV instead is give me information on the scattering at H polarization when I transmit a field in the V polarization. And a similar discussion can be done for the other two elements. Okay. So, for instance, the overall diffuse electric field at the H polarization is given by the superposition of these two incident fields, one in H polarization and one in V polarization, weighted by these coefficients, okay? That are complex coefficients, okay? The scattering coefficients. Good. And so, sorry. Okay. Indeed, we have these two quantities are the scattering coefficients related to the transmission of the H polarization in this formalism, and yet this other one after the transmission of the V polarization. Okay? In other words, these rules the behavior of the diffuse field when I transmit H. This rule the behavior of the of the scattered field when I transmit V. Okay? These two, the principal diagonal elements are called copolar coefficients. These other two, cross-polar coefficients. Okay? Copolar because I observe the field in the diffuse field in the same polarization of the transmission, of course. Okay? Cross-polar because I observe the diffuse field in the polarization orthogonal to the transmission one. Okay? Okay. Some basic properties of the polarization in a very large of the polarimetric scattering, sorry, in a very large number of scenarios due to the reciprocity dictated by the Maxwell equation and so on, we have that these two elements are in theory equal each other, okay? So from four complex elements, if this property holds, we have three complex elements to describe the scattering. Okay? But I also told you before that this quantity can be usefully described as a stochastic process. Okay? So we need to evaluate some second order statistical descriptors. And this can be done by means of the polarimetric covariance matrix, okay? That can be computed by the scattering matrix considering the cross products between the elements, okay? This matrix is Hermitian, is Hermitian symmetric, so due to these properties, these are the non-redundant elements. That is, if I have this, I don't need to measure this because equal to this one, and the amplitude of this element is equal to this one, but the phase is opposite, and so on. Okay, these are complex. Out of the principal diagonal are complex elements. Okay. This is the total received power. These elements allow us to define the total received power of the polarization data. And as I told you before, if no energy moves from H to V, I will doubt that this element is zero. In this case, I will not have cross polarization in the data, okay, in theory. That is, no energy moves from V to H and vice versa, okay? Similarly, if there is no depolarization between the two polarimetric components of the electric field, I will measure zero for this quantity, okay? That is, sorry, one for this quantity. The complete depolarization is given by zero for the correlation between the HH and VV channels. Okay, in this case, these channels, these scattering channels can be considered as independent. Okay, no information about VV can be given if I know HH and vice versa. Okay. Other properties can be about the scattering can be given analyzing these coefficients. For instance, another property that can be often observed in actual data is the reflection symmetry. When the copolarized channels, the correlation between the copolarized channels, HH and VB, with the cross-polarized channels is zero. Okay, these symmetry properties allow us to extract extract information, see things about the targets in the scene. Okay. Similarly to the covariance matrix, we can consider the coherency matrix that can be obtained rearranging in another way the elements of the scattering matrix. Okay, the two matrices are somewhat equivalent. Okay, sometimes it's convenient to use the coherency matrix, sometimes it's convenient to use the covariance matrix. And again, we can list all the properties due to the Hermitian properties of this the T matrix, the coherence matrix. These are the non-redundant elements and so on. Okay, an example. These are data acquired again from the P-band polarimetric SAR system developed by us and mounted on board an helicopter. And these data were acquired on the Morocco desert. Okay, just to show you some the properties I told you before on actual data. Okay, starting from the 4 channels measured by the system, I can analyze the elements of, in this case, the covariance matrix. That is, look, HH, look, this essentially this element and the correlations between the elements of the scattering matrix. Okay, of course, I can say the correlation between HH and HH itself is 1. Of course, no, this is not the power. It's the correlation. Okay, will be SHH, this quantity over SHH. Okay. Instead, the correlation between one co-polarized channel with the 2 cross-polarized channel is very low. Look, in this case. Or similarly, the correlation between one copolarized channel with the other copolarized channel, HH versus VV, is really high. Okay? Just to give you an idea with actual data of these properties. Okay? Okay. Okay. Couple, high correlations in general, good degree of polarization in this case, no depolarization, more or less, and reflection symmetry. Okay, the correlation between couple and cross-pole channels is quite low. Okay. Okay. What we said? We said that the characterization of the scattering can be made through the scattering coefficients that allow us to link the incident field to the diffuse field, or vice versa, better, vice versa. The diffuse field to the incident field, basically through these quantities that depends just on the scattering, okay? Theoretically. But as we said before, what we measure at the receiver side is not strictly what we want to see. It's not strictly the normalized radar cross-section or the radar cross-section of the scene, or the targets in the scene. Why? Because somewhat what we measure depends on the characteristics of the sensor through the antenna patterns, through the transmitted power, and also on the acquisition geometry through the range decay and the let's say the dam, but actually the dam seen by that particular acquisition geometry. Okay, this projection from the ground to the radar plane depends, of course, on the topography, but also on the acquisition geometry. If I fly along one direction and then I fly along another direction, I will see two different scenarios, okay? And of course, this geometrical factor will change. Anyway, we are interested to get the scattering coefficients and the quantities related to the scattering coefficients, like the polarimetric correlations or the NRCS. But we don't measure strictly this at the receiver side. Okay? We can resort again to the link to the radar equation and say, okay, as we did before, we have to remove, to compensate at our best, the factors that do not depend on the scene, so the NRCS, but depend on the radar and on the geometry. Okay, so we want to compensate at our best the things that are the factors that are introduced by the radar, the device, the physical device, the antenna pattern, for instance, or the processing gain, or this factor, and the factors that depends. At our best, we want to compensate the factors that depends on the acquisition geometry. Okay. This equation is similar to the one I presented you before, but it changed from the other one for these factors, the PEDEX, the subscripts, of course, PQ, because these quantities with the subscripts PQ depends on the polarization. So we can repeat what we did before if we suppose that these informations are available. For instance, I know the antenna patterns, or I'm able to calculate the range to target, the radar to target distance for every target. In this is not so trivial because, for instance, in airborne SAR data processing, we need to get the focused data and then the calibrated data. We need to get to use to focus the images. We need the digital elevation model and the navigation data recorded on board the aircraft. Otherwise, I will get very low, very poor focusing result of the data. Okay, so these things are not. What happened? I think. Okay. I'm here. Sorry. If I suppose, as like before, to know these quantities, the antenna patterns and so on, I can perform the polarimetric SAR data calibration quite easily. Polarimetric SAR calibration, because these quantities may change over between the different channels. Okay. For instance, I can use an antenna to transmit in H and another antenna to transmit in V. Okay. Or I can use the same antenna to transmit and receive both in H and V, but the electromagnetic characteristics can change between the two antennas. Okay, just to give you an idea, as usually it happens. And also this quantity. I told you before, this quantity is related to the hardware gains, losses, and crosstalks. What are crosstalks? Crosstalks is something related to somewhat related to the coupling between a device operating in the H polarization with the device operating at the V polarization. Okay, so this quantity can change between the H and V polarization, and if I am able to measure these quantities before recording the data, I can access to the normalized radar cross section and then to the scattering coefficients after compensating these quantities from the digital numbers that is from the received power at the different polarizations, at the different polarimetric channels, or otherwise, if I don't have access to the information about these factors, I can somewhat exploit the properties I mentioned you before. I don't know, the reflection symmetry, the depolarization degree, the cross polarization degree. I can resort to these properties and estimate these quantities strictly from the measured data. Okay. In other words, starting from these, I would be able to recover these after the compensation of these quantities by imposing the symmetry properties that should characterize the polarimetric data. Okay, there are different procedures to deal with this task, that is for the polarimetric calibration of these data based on the data themselves. But we will not see this in this talk. If you are interested, you can tell me, I can suggest you some paper. This was just to tell you that as you need to calibrate the data, even if you are not interested in the polarimetric processing, you need to calibrate the data also and especially if treat with data acquired at different polarizations. Okay, is very, very, very important, among the most important processing step to perform if you have to work with polarimetric data. Okay, in the following we suppose to have already calibrated data. That is, we don't care about this. Everything is perfect. We measure what we want to measure. We measure what we expect. Okay, no impact on the not strong impact on the sensor characteristics like the antenna patterns on the projection and so on. Already done. Okay, we are just watching at this. Okay. Okay, based on these aspects and based on what we told up to now, we saw that, okay, if I have a set of polarimetric data acquired at different polarization, hopefully in the 4 polarimetric channel, and so have the complete scattering matrix, I can combine this quantity to retrieve information about the scene. Okay, but the scattering, I told you again, is quite complicated. I mean, what happens when a wave at S band or at X band or at L band impinges here and then goes back to the sensor? Okay, what happens in the middle? Only Jesus knows. We don't know this. We can just rely on what we measure. Okay, so again, we have to find something simple to discriminate the most fundamental aspects of the scattering process. Okay. In doing so, after the calibration, after polarimetric calibration of the data, you can see, okay, it's true, the scattering from the targets, it's quite, depends in a quite complicated manner on both the radar and the scene parameters. Okay, lambda is the wavelength, theta is the look angle, epsilon for me is the permittivity, the permeability, S and sigma. Sigma now does not stand for the radar cross section, but represents the roughness of the target. Okay, a different scale, and the scattering S, the scattering coefficient, depends on a number of parameters, radar and target, a number in a very complicated manner. We want to combine the data acquire different polarization to get to say something about the target. And in this comes to help, in this task comes to help us a theorem, the target decomposition theorem. Okay. Any target may be decomposed into the sum of 3 single targets. That is, whatever is the distributed target, we can consider it as equivalent to, as a scattering point of view, 3 elementary targets, okay, to extract its basic features, okay? What this means? This means that I don't care for now or how is complicated this function. Maybe I don't know this function, okay? On how the scattering depends on the radar and in scene parameters. I resort to this theorem, and based to these matrix, for instance, or to the elements of this matrix, I can consider the decompositions, the polarimetric decomposition of the targets in the scene. What does this mean? Okay. For each pixel in my image, I can, after the statistical mean, that is after the multi-look. Do you know multi-look, guys?
Yes, we've seen.
Okay, thank you. If I assume that the electric field is an ergodic process, I can change this statistical expectation with the average operation over space, so with the multi-look, and from my polarimetric dataset, compute these quantities, okay? In particular, for one kind of decomposition, the quantities of the diagonal of the coherency matrix, okay? In particular, if you go to study the scattering from canonical targets, like for instance, flat plate or I don't know, corners or dipoles, we'll say that, for instance, in the scattering from a flat surface, the H polarization is in phase with the V polarization. Okay, so if I consider this element of the coherency matrix, I will see that this element would emphasize the surface scattering, or more in general, the odd bands scatterings. That is, one band is a surface scattering, three bands, one through another plate here will be three bands, and so on. Odd band scattering is emphasized by this combination of the polarimetric scattering coefficients, because H polarized waves and V polarized waves are in phase when they come back from a flat surface, or more or less, or something that is similar to a flat surface. Instead, if I consider the scattering from a canonical object similar to a corner, I will see that the H polarized wave goes back to the receiver in phase opposition with respect to the V polarized wave. So that if I compute the difference between these two polarimetric channels, I would emphasize the scattering from even bands as a diagonal or a corner targets. Okay. Instead, if I consider the scattering from dipoles, I would say that part of the energy from the V channels move toward the H polarization and vice versa. So, for canopy scattering that I can represent like dipoles, usually I observe that the cross pole element of the scattering matrix, SHV, is high. Okay? So, starting from the amplitude and the phase on the HH, VV, and HV polarimetric channels, based on a simple combination of these channels, due to these reasons that comes from theoretical consideration about the scattering from canonical objects, I can see, okay, if I get a polarimetric dataset at all the channels HH, VV, and HV, if I combine the channels in this way, if for instance I make the modulus, the absolute value of HH plus VV, make the squared value, and make the multi-look, I can emphasize the surface scattering. I can emphasize the double band scattering with this operation, and the canopy scattering or volume scattering with this operation. Okay, so I can obtain the so-called polydecomposition of the data. Okay. Just before explaining the other one, I want to give you an idea. Okay, let's consider this data acquired at S-band from an airborne SAR. The data has very good resolutions. These data were used, were acquired by this sensor that was the demonstrator of the NOVA SAR S sensor, the first SAR sensor developed by the UK Special Agency, and I work with this data 10 years ago, or less, more than 10 years ago. These data were used to demonstrate the capabilities of the S-band. There are not a lot of S-band sensors, maybe two. One is Novasar from the UK, and the other one, I don't remember the name, but it's from China. So S-band is not very investigated, not very used from SAR applications. Before developing the sensor, the satellite sensor, people from the UK Space Agency, of course, wanted to test the capabilities of the S-band, and in particular, the capability of the S-band from a polarimetric point of view. So they acquired a huge data set from an airborne SAR, the demonstrator at S-band, and analyzed this data. I was in the team at that time to do this, and these are the one channel, the HV channel of an acquisition close to a landing strip, and this is the poly decompositions. Okay, what you can see about this image here. Okay, by visual inspections, you can see, okay, if we are used to deal with to see SAR images, you can say, okay, darker areas are usually relevant to highways, streets, see spots, things that targets that has a low backscattering. Okay, if you are used to see SAR images, you can say this. Okay, this is a strip. Actually, this is the landing strip, okay, of an airport. This is on the both sides of the strip, bare soil, probably. These are buildings that appears as bright points, and this instead is, I think, a forest or something like this. This looks like a photo. Very good resolution data. Okay. So streets, forest, trees, buildings, and so on. Okay, if I'm used to to deal with SAR images, I could see, okay, this is a building, this is a street, no, this is a landing strip, this is a forest, this is a shadow, or I don't know, this is a tree strip, and but if I'm not used or I want to make a classification in unsupervised and fast way, of course I have to devise something. I can devise something, for instance, based on the polarimetric characteristics of the data. And a simple way to combine this is the poly decomposition I showed you. Indeed, from this data, this is the HV channel, considering also the HH and the VV channel, combining them in this way, I can get this. Substantially, the surface scattering is given by the green pixels. The blue pixels instead are representative mainly of the dihedral double band scattering, that is scattering mainly from buildings, man-made targets that have corners, while the red pixels are representative of volume scattering, that is scattering can be represented like a cloud of randomly oriented dipoles. Okay, something confused. Okay, just to give you an idea on how I can combine polarimetric data for the mapping of the targets in the scene. Okay, from this to this. Blue. Very quickly you can see, okay, buildings or something like buildings. Or also if here we were considering a C spot, green is C, count C, blue sheets, okay? And so on. Okay, just to say you, okay, from the polarimetric combination, according to the poly composition, I can move to this, where I have to inspect if I am an expert or I am used to see sub-data to say, okay, this is a building, forest, I don't know, a field for agriculture, to this. Okay, green surface scattering, blue buildings. Okay, this could be useful, for instance, okay, I want to discriminate from rural or natural or man-made areas. Okay, I can discriminate quickly using this kind of approach. Of course, one has to handle with the false alarms, okay, because a tree can be also give rise, the trunk of a tree can also give rise to double band scattering, but this is true if the wave is able to comes through the foliage to the branch of the tree, and so to reach the trunk and go back. Instead, at test band, I can see, okay, substantially as band 3 centimeters, no, 4 centimeters maybe of wavelength, more or less wavelength. I can I'm quite confident that the wave does not penetrate the foliage layer, the branch layer of a tree, and so you will not hit the trunk. Okay, so for instance, in this case, I do not expect the double bands scattering from a trunk, and I'm quite sure to ascribe this to a building, for instance. Just things, just examples. Okay, and this is one kind of decomposition that is very commonly used to represent the fundamental scattering mechanisms occurring in the data relevant to a scene. Okay. Another one very used, also based on the elements of the coherency matrix, is the Claude or H alpha decomposition. Okay. We know that I told you before that T is an Hermitian symmetric and positive semi-definite matrix. So we can consider the decomposition in eigenvalues and eigenvectors. Okay, so we can consider this matrix with these elements. These elements you can measure with for the data. We can construct, again, I tell you any element of this matrix through the data you have access from your full polarimetric dataset. And from this matrix, you can consider the eigenvectors and eigenvalues matrix. Or in other words, this. Okay. And this expression means that this 3x3 matrix can be decomposed in 3 as the sum of other 3 matrices, T con E, weighted by the eigenvalues, lambda con E. And this formalizes substantially what I told you before through the target decomposition theorem. Any distributed target may be decomposed into the sum of three single targets, okay? This is a way to formalize this, okay? Anyway, considering the eigenvalues and the eigenvectors, which has this form, and are in particular characterized by the scattering angle. Any eigenvector can be written like this, where alpha e, where the subscript e stands is equal to goes to 1 from 1 to 3, is the scattering angle representative of the main dominant scattering mechanisms for that that elementary scattering process. If we consider this decomposition, that is again from the T matrix, the coherency matrix, we consider eigenvectors and eigenvalues, we can compute from these quantities the polarimetric entropy and the mean scattering angle. Allora, the entropy, the polarimetric entropy, like any entropy, in particular like the information entropy, give you a measure on the degree of confusion that characterize the observed scattering process. In particular, the higher the H is, the more confused the scattering process is. That is, if H tends to 1, have a very confused scattering process. This means I can mix it in the wave I receive the contribution arising from trunks, from buildings, from not homogeneous things. Okay, it's very confused, the scattering process. Conversely, if H tends to 0, goes to 0, so very low entropy, the scattering process related to the pixel I am observing, I am analyzing, is quite deterministic. Okay, I can say if H is approaching to 0, okay, I expect that in this pixel there is one kind of dominant, well-defined scattering mechanism. Then it could be relevant to double bands objects like trunks or buildings, or I don't know, but or instead could be related to surfaces, or I don't know. But there is one dominant kind of scattering process. Which one? The one defined by the value of the mean scattering angle alpha. If you go to study the properties of this decomposition, that less intuitive of the poly one, you can say, okay, if alpha goes to 0, I can see to 0, I can say that the scattering is similar, the scattering mechanism I'm observing is similar to the scattering from surfaces. Instead, if the scattering, if the value of alpha is close to 45 degrees, is representative of scattering from dipoles. Instead, if scattering is close to 90 degrees, the scattering is representative of double band structures, corner diagonal structures, okay? And of course, you have the keys in the middle. Okay, so starting from the eigenvalues lambda con E and the eigenvalues U con E, from which we can get the scattering angles and the mean scattering angle, we can define alpha, the mean scattering angle itself, and the polarimetric entropy H. The Claude decomposition, also named H-alpha decomposition, is based on these two quantities. Okay. In practice, I can split the H entropy alpha means scattering angle plane in these regions that are 9 regions, and based on the values assumed by the couple H alpha, I can say, okay, if for instance the alpha angle is between 0 degrees and more or less 40 degrees, I am observing pixels that are related to electromagnetic energy arising from targets that can be ascribed to surface structures. Okay. Instead, if I am measuring the alpha value and the values are between, I don't know, 45 and 40, something close to 50 degrees, I am observing the pixel I'm observing are relevant to structures that behave like whose scattering behave like volume structures. And finally, the same discussion also for the double band scattering in this region of the alpha, or the values of the alpha angle. Depending on the values of the entropy, I can say, okay, more chaotic, less chaotic, deterministic scattering processes I'm observing. Okay. Okay. Differently from the poly decomposition, this one is Hénard decomposition. Okay. In the poly decompositions, for any pixel, we had a value for the double bands, a value for the surface, and a value for the volume scattering. So I have an RGB in the color map I showed you. An RGB code for any pixel. So is a soft decomposition. I'm telling you that, for instance, for this pixel, the value of the surface scattering is 30%. The value of the double bands is 40%, and the value of the volume scattering is 30%. Okay, so that the final color I see in the polymap will be given by the 30% of red, the 40% of blue, and the 30% of green, that are representative respectively of volume, double bands, and volume and surface scattering. Instead, in this case, I have a hard decompositions. I cannot say in this part for a pixel that measure, where I measure H equal to 0.7 and alpha equal to 30 degrees, I cannot see. Here I have 30% of volume, 20% of I don't know, surface, and the rest of double bands. Now I can say, okay, 30 degrees alpha is equal to 30 degrees, okay, surface. Then depending on the H value, I can say, okay, high entropy, medium entropy, less or more or less chaotic, but I cannot say is this quantity related to surface, because it's an hard decomposition. Okay, just, in other words, just 9 colors, not a continuous combination of colors like the ones given by the polymap, in the polymap. Okay. Okay. So again, this is the example, the data set I already showed you, the poly decomposition, and this is the cloud decomposition, okay? Somewhat they provide similar results. In this case, scattering in red, volume scattering in red, surface scattering in violet, while here in green. Okay, similar results. I can consider this or this decomposition that are very common and use a decomposition to classify the scattering mechanisms occurring in a observation. Okay, and just to give you an example, at the time of the radar data acquisition from the aircraft demonstrator or the Novas RS, people from Astrium, that was the agency, not the company actually, that was involved in this kind of data acquisition and also for the development of the radar, made an info campaign to have to retrieve, to construct a ground truth map of the scene observed by the sensors. So, for instance, in this site, they classified the cultures, the agriculture fields with respect to the kind of plants, grass, wheat, rapeseed, barley, maize, and so on. And the same classification has been made through the radar data, through the Pauli and cloud decompositions, and we combined the field, the radar response at different from the different decompositions and from the different fields to see how radar response similar arising from distinct fields, distinct from a physical point of view, but similar from the cultivation point of view, can be classified using the data acquired at test band. And so we found this kind of results. More or less, we found good results. For instance, unexpectedly, we found that the maize chocolate, I don't remember, chocolate in Spanish maybe, fields give rise to high value or double or surface scattering. Instead, we found, okay, this kind of plant at test band should be seen as a double band scattering. We were investigating this kind of aspect. Why this? Then we asked to the people who made the ground truth, who collected the ground truth. No, the maize field was labeled by how like maize field, but at the time of the acquisition, the plants were already cutted. So okay, the method seems to work. Okay. And this kind of classification and clustering can be made for, I don't know, application of precision farming and so on. Similar results were obtained even at actually slightly worse result by considering the H-alpha acquisition, but just to give you an example of what we can do with very simple. There are actually a lot of more complex and involved methods to provide also unsupervised classification. Anyway, just to give you an example, an idea of what you can do with the polarimetric data. And I will take a break before starting with the soil monster. What do you think?
Yes, I think we can stop for lunch. In Argentina, it's lunchtime. And maybe get together in an hour or something like that. An hour and a half. You tell me, Anthony.
Okay, perfect.
I don't know. Do you think we should get together in an hour or you
No,
need
for me it's perfect. We can, if we can, are you asking me if we can stop? If we are able to finish in an hour? I don't listen.
know if we can stop?
No, for me it's perfect. Starting in an hour again.
We start
Okay.
again in an hour. Okay. ¿A todos les parece bien? Nos volvemos a juntar a la 1.
Bueno, me parece bien.
Sí. Bueno, voy a parar la
Perfecto.
grabación. I'm gonna stop
Nos vemos
recording
a la 1.
for this time and we'll start again in the afternoon.